Thanks.
Thank you for the introduction, and let me also thank all KITP for having us here. It's been really great to be here last month, at least for me, during this program. KITP is a really great place to do science, and I guess that all of us will regret going back to our normal lives after this program. So what I would like to do today is to give you an overview, so a very partial overview given the time constraints, so I apologize in advance if I'm not going to cover all the many facets of this field, this exploding field to some extent. But I'm going to cover some of the things that have been discussed during this program and also during the conference, and which are mostly about using techniques, so machine learning techniques, to study and to do some progress in many-body quantum physics. So it's clear that here we have two main ingredients, right? So the first main ingredient is machine learning. I guess that most of you are familiar with the concept of machine learning, but it doesn't hurt to do a general refresher. So machine learning techniques are highly successful computational methods that in the past years, I would say in the past decade or so, have allowed to improve substantially on a lot of technological, practical applications, right? So typical examples where machine learning has helped a lot, and I would say especially deep learning applications. So actually in the following, I will mostly concentrate on this very specific framework of machine learning, which is deep learning. So I'm not going to discuss all the possible cases of machine learning. But in this case, we know that deep learning in practical applications has allowed us to do substantial improvements on existing state-of-the-art methods, for example, in applications such as speech recognition or image recognition. Right? This is a standard, one of the applications where we've really seen some substantial advantage in using this kind of numerical approaches which are based on deep networks. So, for example, around 2012, 2006, we've already started seeing some improvements, substantial improvements over the existing state-of-the-art. But the most important to me is that these kind of techniques, so again, industrial inspired techniques, have allowed us to do some applications that were not at all possible before the advent of this kind of technology. Examples in these directions are, for example, applications such as self-driving cars, right? So if you own a Tesla, and in California there is quite a few Teslas around, you know that this kind of technology is somehow becoming more and more common in this kind of cars, with some caveats. This kind of applications is becoming possible, were thought to be somehow much more distant in the future than they actually are now. I mean, they are with us now. And also very intriguing applications such as game playing, which are to some extent much closer to the notion of general artificial intelligence than these very specialized applications that we have here, have been made possible thanks to let's say, deep learning, especially around, this is, for example, the year when we've seen the first artificial intelligence, which is, in this case, AlphaGo, be able to beat the world champion in the game of Go. So Go is a very complicated board game with much more complex tactics than chess. And for the first time, let's say, in the history of humankind in 2016, this artificial intelligence built on deep networks was able to beat the world champion in Go. So we've seen real, actual, tangible progress in this kind of technology, which to some extent has led to several breakthroughs in several practical applications. Now, given that the scientists typically are not completely, outside of the world, I've noticed that this has happened in the past 10 years, and I've tried to figure out how can we use this technology in, let's say, more fundamental research, right? So one of the applications that have been put forward, okay, let me put it here, that are being put forward in the last couple of years. I mean, to some extent, depending at different speeds, depending on the different fields, especially. We have seen a lot of applications of these ideas to problems in science, and you can see that if we look at this and we look at the variety of applications where deep learning has been successful, it certainly makes sense to try to understand what deep learning as a technology that we can certainly improve as scientists can do for us in the domain of science, right? So, and during the conference, we've seen applications that range from, astrophysics, high-energy physics, condensed matter, string theory, chemistry, and of course, quantum physics. So, all sorts of sciences these days are living a truly, machine learning revolution, where we are trying to figure out what these techniques can do for us and how we can improve what we are doing with other approaches. Okay. So what really underlies the success of this deep learning technology, to a large extent, is the fact that we can, is the fact that these problems have in common a simple observation. So the fact that all these problems, if we want to really solve them, can be written as function approximation problems. So here we are dealing with a very high-dimensional function. For example, a function that solves the speech or image recognition problem can be thought as something that takes, so let's say that I have now a function that takes some binary variables, b1 up to bn, where these binary variables are nothing but the bits of information that I have, in a given digitalized image that I have on my computer. Then, for example, having a machine that is able to discriminate and basically to tag images, or to say that in this image there's a person with some name, so that's what Facebook does for you, is equivalent to saying that I want to find a very high-dimensional function that for an arbitrary input, which is this image, is going to return, let's say, a name. So let's say, this case would say that Tom is in this image. Tom is my idealized version of a man, but you can't see it very well from it. Right? But, so this is a very simple example, but you can immediately understand that this problem of finding high-dimensional representations of complicated functions, low-dimensional representations of high-dimensional functions is extremely important in a variety of domains. So, for example, if you wanted to translate a string of text, right, from English to French, right? So, Francis, just to make it a little bit more French. So you can see that also the goal of translating from one language to another can be written to some, with some mathematical function f that takes a string and translates it into another language. So if I am able, through, for example, learning, to find a good approximation of this high-dimensional function, I'm then solving basically all this problem that I'm writing here, right? So this is the mathematical underlying problem, and also in science, as you know, and as Feynman has told us, the basic equation that we want to solve is this one, u equals 0, where u is an unknown function that we want to basically identify, right? So basically, in all of this, we are dealing with functional approximation, and we'd better be able to do functional approximation well, right? So the way that deep learning approaches functional approximation is through basically deep networks. I apologize for my handwriting, which is horrible since the elementary schools. So basically, deep networks are nothing but a compact way of parameterizing high-dimensional functions. So basically, consider again the simple case of some f of x. The way a deep network parameterizes this high-dimensional function is relatively easily. So you parameterize it as a weight, some weight matrix that I'm going to define in a second, times some activation function that I'm also to define in a second, which is applied then to another layer, then to another activation function, up until to the point where you reach the first activation function, which is applied on my first layer, weights, and then on my initial input x. So what does this notation mean? Well, first of all, this index D that I've defined here is typically known to be the depth of the network, so which is basically how many times I'm applying this operation, right? So these non-linearities. And indeed, these sigmas are nothing but, so let's say the generic sigma I would be a one-dimensional function, which is typically a nonlinear function, so-called nonlinear. It's just a nonlinear 1D function, which in jargon is called activation function for a reason that I will clarify in a second. And the only other thing that characterizes this basically parameterization of the dimensional function are those weights, basically, so those matrices that that this index D, so I, that I have D of them, and basically those are matrices that are typically, but not always, taken to be real, with some width that I call L basically of sites Li times Li minus 1. Okay? So, and these objects are the other important thing that fully defines the neural network. Those are called the widths, basically, of the neural network. Okay? So people like to write this thing in terms of diagrams, and the way people like to write this is in terms of some input variables, which are these x variables that in this case live in an n-dimensional space, right? They connect them to some other degrees of freedom at the subsequent layer. So this would be layer 0, or where I'm applying this matrix of this vector, layer 1, layer 2, etc. And basically these degrees of freedom are constructed to be just the application of this activation function, for example, in this case sigma 1, to a linear combination of these input vectors. So what this writing is telling us is that we are taking a linear combination of these objects with a matrix W and then feeding this input into this other degree of freedom in the next layer. So we basically write something as simple as sum over j of wij xj, and then the output is basically the result of this variable here. And then we can do the same for other variables. And what defines the width of the network is how many of these objects I am considering at each layer. So in this case, this would be 2, and this is so basically L1 will be equal to 2. In this case, the depth, the width at the first stage will be equal to the number of variables L1, and so on and so forth, until composing this nonlinear function a lot of times, I reach the output of my network. Right? And the output of my network will be simply the last layer, LD, and those quantity will correspond to basically the result of my function, which in general can be a vector function. Okay? I guess that some of this is already very well understood by everybody here, but just to put ourselves on the same page in terms of notation. Okay? Now, why is this form somehow interesting, and why do we want to use this in the real applications? Well, there are at least 2 reasons or motivations, I would say. So the first one is that these kind of architectures are loosely inspired by the physiology of the brain. So in particular, you can think of these objects as some idealization of a neuron in the brain that are receiving some electric signal from a lower level layer of neurons. And the interpretation then is that when this signal, so when the sum of the incoming signal is larger than a certain threshold, basically what this activation function, sigma x, is doing is that it's basically telling if the output should be somehow finite, 0 or some finite value, if the incoming signal is larger than a certain threshold. So this is typically what a typical activation function does. It is, again, loosely inspired by the physiology of the brain. So in practice, this is a very loose and very bad description of how a brain actually works. So it has to be understood that this is just a convenient mathematical form to describe what a deep network is. And indeed, to some extent, this is only a very simplified version of an actual neural network. But to some extent, I mean, we are somehow justified to do that in the sense that, for example, when we got inspiration to build our planes, we looked at birds, and we saw that birds had somehow wings, but the wings of birds are movable, right? Instead, the final somehow paradigm for actually working planes do not have movable wings. They have just rigid wings that are actually also more powerful than what nature would have suggested us to start with. So our goal here is not to mimic the behavior of the brain, but just to use a very lousy, if you want, description of the brain that we want to use for our applications. Okay? So this is a deep network. And the other, so the first motivation why this should be, somehow plausible, I mean, useful, is biology, right? So biology is telling us that this is the way, roughly speaking, a network in a brain should work. The second reason, which to me is somehow more important, is the fact that this kind of functions, this composition of nonlinear functions, are highly expressive ways of representing complicated high-dimensional functions in a compact way. So even though we don't have a general mathematical framework to describe all the cases in which this happens, we have half proofs that for a physicist like me are somehow a full proof. And in this sense, I like very much the result by Kolmogorov and Arnold, who actually didn't work on machine learning at their times, but to some extent they did it afterwards when we revisited their results. But basically what Kolmogorov and Arnold shown in their famous representation theorem which is somehow a hint to the fact why we should use this kind of functions, is that if you have a very complicated, possibly infinitely complicated function that, let's say, translates from English to German or whatever, so a very high-dimensional function of n variables, then it is always possible, always means with the condition that this function is continuous in its input variables, to find a network, basically representation, written in modern terms, which looks like this. So if you look at their theorem, you can realize that what they are saying is that it is always possible to write a neural network, a deep network, which has n inputs, basically these variables x, then a deep layer that I'm not going to draw all, but this deep layer contains order, basically n square neurons, okay? And then another second layer, which contains order n neurons. So if you want, the width on the first layer is n squared, so on the zero layer is n squared n order. And then, since we are trying to approximate basically a scalar function, you know that the last layer should contain only one output, which is in this case basically just one. And the activation function that they consider are, let's say, in general, sigma 1 of x, so on this layer, sigma 2 of x on this other layer, which in general are two different one-dimensional activation functions, and on the third layer, this is the only one which is very simple, which is the identity. Okay? So the claim, what this theorem basically states is that an arbitrary high-dimensional, infinitely complicated function can be written always in this form. And to me, this is a hint that we can use these kind of architectures to at least try to hope to represent these things more carefully. Yes?
So presumably the theorem states what the error is as a function of n?
This is an exact representation of the functions. So the problem, of course, is that representing, this is sigma 1 and sigma 2 somehow hides the complexity of the original function. So that's where the catch is, and where, of course, this is not a full proof that machine learning is solving all the problems in the world. But this is a hint to the fact that if we use a functional composition, we can represent more compactly, at least hope to represent a high-dimensional function, as opposed to, for example, this is the thing that I wanted to mention here, writing a representation of my f of x in terms of a finite basis. So imagine that I wanted to do let's say, a Fourier decomposition of my original basis, original function, what I would really need to do is that I would need to define all my coefficients, C, K1 to Kn, if these are my wave vectors, let's say, times some basis function that is phi of k, so it can be, let's say, the product of my Fourier basis components. So you know that here, in the worst case, so in the general case, let's say here, if you have an n-dimensional function, you need exponentially many coefficients to describe a generic function. So there's really no hope in general that you can represent this complicated object with a linear combination, unless you are very lucky. Whereas if you use this representation, at least there is hope. Now, the problem is, of course, finding the sigmas, but at least there is hope that you can do that.
So you trade n for the simplicity of sigma 1, sigma 2?
Yeah. So basically, if you want to then generalize this thing to the realistic case, you have to trade. Yes, you have to approximate these things with something you can compute efficiently, and then in that case, you get basically Sibbenko's results where this object, this n can be in general exponentially large. Yes, but that's of course. I mean, there's no free lunch, and this is actually a statement of that. But what I want to say is that if you start with an actual linear combination, there is really no hope from the very beginning. Okay. Now, this is a hint to me that these kind of things, to some of us, that this can be used to do also, to represent the general complicated functions. And indeed, what are the complicated functions or the complicated problems that we would like to study with this kind of approaches in the context of, let's say, many-body quantum physics? So the idea is that, somehow inspired by these results that have been obtained in the industry and in a lot of practical applications, we would like to find a natural application for these ideas to quantum physics, right? So, and this brings me to the concept of neural network quantum state. Quantum states, which are, to some extent, a natural version of the extension of this idea to the quantum world. So you know that if you have a quantum many-body system, the basic object that you need to describe all the properties, in principle, of this quantum many-body problem is the wave function, right? So the wave function of the system is basically what contains all the amplitudes, all the coefficients that you need to compute all physical properties, all the, if you want, the time-dependent behavior of your system, everything is contained in the wave function. And to some extent, this object is it's sort of monster living in a very high-dimensional space, which is way too large than what you would expect from some regular standard quantum system, which is the Hilbert space, right? So, for example, let's consider the case of simple, let's say, spin system where my quantum numbers are, let's say, plus or minus 1/2, right? So here I'm dealing with a quantum spin 1/2 system. Those degrees of freedom can be plus or minus 1/2. And even if I consider a moderately small quantum system, which has, let's say, n equal, 50 or 60 spins, right? You can immediately realize that in general, the number of coefficients that you need to fully determine the properties of the system is 2 to the n. Right? So basically, in this case, 2 to the 60, which means that on any practical applications, on any practical computational applications, or also in any theoretical application in most cases, you are unable to store all these amplitudes that I am calling here psi of S1, S2 to n, simply because there are too many. So there is no way you can solve exactly, let's say, Schrödinger's equation for more than 40 spins. There is no way you can solve for dynamics. We have to do some approximations. And that's where these powerful techniques can help us with. Okay? So how can they help us with? How can we somehow be helped by machine learning? Well, the idea of neural network quantum states is, at this point, straightforward. What you want to do is that you want to represent these wave function amplitudes as an artificial neural network. Okay? So what we do is that this is a high-dimensional function, a complex-valued function. We are allowed to do that. We also have some guarantees that any arbitrary function can be written in this form. So why not? Right? So we do that actually for reasons that I cannot explain here easily, we parameterize the log of the wave function rather than psi itself, but this is a technical detail, with a neural network f of s up to s, okay? Which is parameterized by some weights and by some network structure that we have somehow fixed a priori. So why do we want to do that? Well, first of all, because as I was mentioning before, solving this, having a compact representation of the wave function is very helpful in general when we have a large or relatively large amount of spins and where we cannot solve this problem, where we want to represent the physical properties of a system exactly. So we want to have a compact representation of this system. And this is a compact representation. So this is the first reason. So when n is large, we want to find good approximation to these quantum systems. The second reason, which somehow is written here, is that these representations have shown that they are able to study intrinsically and very diverse problems in a unified framework. So there is good hope that we have this, that we can apply also these techniques to quantum systems. So unified framework. They've shown that they could basically improve on all existing techniques. Can we do the same here for quantum systems? So this is the open question. And the third thing that somehow came after we introduced this representation is to understand what are the physical properties that are encoded in this kind of states. So what are the improvements that we can do, for example, with respect to other existing representations. So, and in this context, so let's say the physical analysis of quantum states, there's been several intriguing results. So let me just show you, let me just list two of them basically. So the first category of results is the fact that if you have these representations, it is possible to write exactly, and by exactly I mean that you can write down all the activation functions analytically, all the weights and everything in an analytic fashion. Basically all, or I mean at least many families of quantums, of topological quantum states. So, for example, in the first work by seminal work by Juan Carrasquilla and Roger Merco, they showed that there is a convolutional neural network, which is basically this, but with some families of weights that are different. You can describe, let's say, exactly the ground state of Kita F's toric code in 2 dimensions. So for those of you who know this model, this is also very important for quantum error correction. It has been also shown later that it is possible to describe exactly all sort of, let's say, Laughlin states. And also more recently double semion models. I mean, all sort of possibly complicated states of matter where you have topological properties and for which we know the exact wave function representing these properties. People have found analytical representation of this wave function in a unified framework that allow us to write these states exactly. Okay? So there's much more results that I'm not able to present here, but this is just to give you a rough idea of what people have been doing. And the other thing that has somehow been also a boost to the research in this direction is the fact that these states can efficiently encode entanglement. So it has been shown by several people. So starting, I believe, with the work of in the group of Dassarma, especially by Dongling Deng. But also Lei Wang and co-workers, and many other people, for example, in Ignacio Sirac's group. So those results are all from 2017 up to 2018. So those are all very recent results. But what they've shown is that because of these long-range connections in the network, so basically you see that in principle I can entangle any of these physical degrees of freedom with any other, mediating these interactions with these hidden degrees of freedom. because of these long-range correlations, it is possible to very efficiently encode the volume law entanglement, especially in high dimension, with a polynomially large number of parameters. So this has to be opposed, for example, to other descriptions where typically, in some tensor networks, where describing a volume law efficiently typically needs an exponentially large number of parameters. Okay, so this is also a motivation why we want to study this kind of, to use this kind of representation, especially for critical systems where we have a lot of entanglement. We want to be able to describe this in an efficient and in a compact way. Okay, so far so good for neural network states. So let's go to the first of the applications that I showed in the...
Do you have a question about the exact maps?
Yes.
Because, so these two papers that you mentioned, they show that it is possible to write the wave function exactly, but can an algorithm also learn it if you kind of go about it the kind of blind way?
So in the case of Laughlin states, it has been shown that this is possible. These other constructions are more analytical in nature, so people have not tried actually.
Oh, okay.
But for some of these, people have tried. I believe also for the toric code, right? This has been done numerically, so they've shown. So for these other states, no, this has not been done yet. But this is very recent.
So what is the numerical? The reward is getting, you don't know what the ground state energy is.
Right, so that's exactly. So until now, I've written only the representation, so the function. Now I'm going to show you, or to give you an idea on how we find these weights, which is basically the learning part of the algorithm.
Is there a map of these to tensor network? They're very similar. They're sort of the
right, so the other thing that I mentioned, I didn't mention actually, but there is a mapping that's been done first I believe by Lei Wang and co-workers between tensor networks and these kind of techniques, these kind of approximations, these kind of representations. The point that I was stressing before is that since here we have volume law entanglement, I mean, the simple mapping you can do will give you a tensor network with exponentially large bond dimension. So the number of variational parameters that you have in the tensor network are exponentially large. But this is, the worst case mapping that you can do. But in general, because of this, the fact that we can have volume law entanglement here, the mapping will give you an exponentially large bond dimension in the worst case. Yeah.
And how does this the net react when you change bases?
Exactly. So this is heavily dependent on the basis, and we see clearly cases where some bases are more efficient than another one, simply because you have more information, for example, about the state.
Tensor networks builds in locality.
Right. Here we don't. I mean, not explicitly. Depends. So what we can do is that we can, for example, use what people call convolutional neural networks, where these weights are only locally applied to some subset of filters, and then you go deeper and deeper. So in a sense, this is also a way of bringing in locality in this kind of game. But the point is that using deeper layers, you can efficiently encode the entanglement. So there's a nice paper by Levin and co-workers from 2019, actually. Very recent, where they show, basically that in some families of neural networks, using the depth, you can increase the entanglement, still keeping locality at each layer. Now, so how do we learn the weights? So this is something that I have not specified yet, which is actually very important. So the first application is this dreaming, right? And somehow I wrote. Maybe I was dreaming too when I wrote the abstract, the title. But so what is this dreaming application? So the dreaming application is actually a way of solving the problem, solving a problem which is fairly common in quantum information and in all, I would say, experiments that are able to access directly measurements of the wave function. So in particular, the application here is that I'm given some black box, right? So for a theoretician, this is an experiment. Right? So this is my experiment, a black box. And this black box contains a wave function. So this is my quantum system that I have in the lab. And what I want to do here, and this is the problem of quantum state tomography. I want to find, or I want to certify, for example, that the state that the experimentalist has prepared is actually what he claims to be, right? This is very important when somebody tries to sell your quantum computer, right? So you want to make sure that it is actually a quantum computer. So, and what you do then is that the only operations that you are allowed to do on these quantum systems are basically measurements in some computational basis, I mean, some basis that you have access to experimentally. And you know that from Born rule, that, let's consider again the simple case of spins. If you do a measurement on system, the probability of observing some quantum numbers is given by the square modulus of the wave function. Okay? So the probability of observing some, so you can probe your systems as many times as you want, and the beauty of quantum mechanics, or somehow the bad part of quantum mechanics, is that every time you will get a different result. So for the very same system, there is no, somehow, classical dynamics, there's nothing as far as we know it, and every time you probe it, you will see a different set of quantum numbers distributing according to psi square, right? So this is Born rule. Now, what we want to do is that based on this observation, in this class of applications, we want to reconstruct the wave function that corresponds, that would give us these observations, okay? So that's the first application. So, and the way this is done, and that's why I call this thing dreaming, is that basically you can imagine that you have a representation, F, like given by some neural network, of your, an approximation, let's say, of this probability distribution, right? So you want to find these weights, and the way we find the weights, I won't go too much into the detail, is basically maximizing the likelihood of observing these quantum numbers as opposed to the quantum numbers that my network is generating, okay? So in this sense, we have a dreaming phase where, especially at the beginning of the learning procedure, what this network is doing is that is taking these samples that have been observed experimentally and trying to reproduce them, or trying to come up with an approximation of the probability distribution which is as close as possible to this thing. And somehow this is like a dreaming, because you see these images and you start creating some distorted and somehow approximate images of what you have observed experimentally. So it's like when you see things during the day, and at night time you start dreaming and re-elaborating with your subconscious the images that you've seen. So this is this quantum state tomography application. There's been, so the early application is by, mostly by Giacomo Torlai and co-workers, including myself, Roger Merck, and Juan, in 2018, where we did this for some problems in quantum, basically relevant for quantum optics and also for cold atoms. An important detail that I'm hiding here is that when you have a wave function, you do not want to learn only psi squared, but also psi, right? So you want to learn also the phase, if you want, of the wave function. And the way we do that, so there are two ways of doing that. So the first approach that we use in this paper, so it's directly based on these neural network states. So what we do is that we observe the system in a specific choice of other bases that we can have access to experimentally. So for example, you can imagine that I'm measuring the system in the ZZZ basis, and from this information I can reconstruct, let's say, PZ, so the probability of observing the system in the sigma Z basis. But I can also observe it in another basis, let's say X, ZZZ, etc. So I can call it X1 somehow, right? So I will just collect all the experimental information that is available and somehow triangulate it, so do a tomography, that's why it's called it like this actually, to reconstruct also the phase of the wave function, okay? So this application was limited then only to pure state so far, but this has been nicely extended recently by several people. There's been a work that Juan has presented to us during the conference and during also the program, which is based instead on the idea of using the so-called P of the M's. So basically the idea here is that instead of cherry picking some specific basis, we use a random basis on which we perform the measurements. So we pick a random measurement and then we try to reconstruct the full density matrix, not only the wave function. So there is a paper by, again, Juan Carrasquilla and Giacomo and Roger and Leandro Olita. I'm forgetting somebody, I hope not. So, and it's from from 2019. Okay. So this is the first class of applications, and what it has been shown so far, most importantly, is that it is possible to do tomography for systems that are substantially larger than what you could do before using only, let's say, standard techniques. So the number of measurements that you need here scales much better than in the case of standard tomography. Okay? Now, let me go to quickly move to the other applications. Hopefully I will have time to do that. So the second family of applications, which is the one that is closest to my heart, is the variational applications, so what I call the computing in the abstract, I mean in the title. So here I remember. So here we determine the weights using experimental things. So here what we do is that we are given by Mother Nature the Hamiltonian of the system, the interactions, and we want to find the ground state, or let's say, or solve the Schrödinger equation, for example, to find some reasonable approximation of the eigenvalue equation given by the ground state, right? So what we do here is that we write, again, a parameterized version of the neural network state in terms of these parameters weights, and what we learn, so we try to minimize, if you want, the energy functional EW, which is simply the expectation value of over CW. So this is a variational family of quantum states of the Hamiltonian, right? So you know that by virtue of the variational principle, this object is always larger or equal than the exact energy. And if your variational ansatz is general enough, you can hope that increasing the size of the network, you can approach to some extent with a good approximation the ground state of the system. So this is something that we pushed with Matthias Troyer in the first paper, 2016, 17, depending on when you count. Okay. Now, the important difference between this kind of family of applications and this one is that here we don't have any sample from the external environment. So what we are doing here is really generating an approximation of the wave function and self-consistently improving it without using any external information. So to some extent, this is a much harder approach to finding the neural network state for the system. Okay. Now, what is the state of the art here? Well, in the first works, we've shown that these methods are competitive with most existing with, let's say, in 1D and I would say 2D, with on mostly, I would say, spin, boson, and some fermion with some caveats, some fermion problems in 1D and 2 dimensions. We compare these, we and also other people compare this to tensor networks, to other variational techniques, and found that in most cases those are competitive and find relatively, good results. At this conference, we've seen a lot of interest in this, somehow in the natural benchmark, I believe, to some extent, for the first applications of this approach, which is the frustrated model called the J1, J2 model for the experts in the audience, and there are. So basically, this is an unsolved open lattice problem where you have frustration in interactions which cannot be solved exactly by any other technique. It is a completely open problem where we really want to try to see what kind of improvements we can do on existing technology. So we've seen several results in this direction, both by Federico Becca and the student who's working with me, which is Kevin Chu. Right. And what I find remarkable, even though we've had discussions about this, is that when you compare these results with techniques that have been used and somehow heavily optimized on this problem in the past years, like NPS, PEPS, or standard variational Monte Carlo techniques that Federico has developed in the past years. And these things have been used for almost 20 years to study this open and challenging problem. So basically, in the span of maybe a year, we've shown that these neural network states are already competitive with the state-of-the-art developed in the past 20 years, and in some cases they can even improve the properties that people have found with these other techniques. Okay? So this is already a competitive approach, and I believe, and this is my optimistic side, that in the next year or the next couple of years we will be able to substantially improve and also get decisive proof of the advantage of these states. Okay, so in the last part of my talk, I would like to discuss another application which is slightly different, even though morally related to what I discussed here, and which is not inspiring. So I decided last minute to change this, maybe last night, but it's driving. Okay. So why driving? So we've seen from the beginning that the problem with the quantum manipulation problem lies in the fact that the wave function is an exponential monster with a lot of parameters, and we want to find an approximation, right? However, this exponential complexity, to some extent, is not only a problem for theoreticians, but also for experimentalists, right? In the sense that if you want to experimentally prepare a quantum state which somehow corresponds to what I would like, so let's say the Hamiltonian, the ground state of a given Hamiltonian, so I will go again in my favorite experiment, in my box, right? So and I want to prepare some target state, so psi target, right? And I want that this psi target is the ground state of some Hamiltonian or is anything that I wish. Now, the problem is that experimentally you cannot just tell the quantum computer or everything you have attempted to do that for you without specifying how, but you have to tell basically how you are going there, for example, manipulating a time-dependent Hamiltonian, right? So in your time-dependent Hamiltonian you have some control parameter, which could be, let's say, in the simple case, let's say, a time-dependent field, right? For example, coupled to sigma x, or some other terms that that are available in the actual quantum experiment. And preparing then the target state means that starting from some point A, let's say in Hilbert space, which is my initial state, psi 0, right? I want to somehow wander in this parameter space, spanned by, if you want, all the protocols that I can do here, so basically the time dependence of h of t, and I want to reach some final state, which is my target state, right? Now, the question is, how do I go from A to B without knowing, without having all the information about the environment? And formally speaking, actually more than formally speaking, but mathematically speaking, this is to a large extent equivalent to the problem of driving a car from a point A to a point B without crashing yourself against a wall, right? So, what has inspired a lot of research in this field is indeed the technology that people are using for to devise self-driving cars or to play Go, which is this technology that is known as reinforcement learning. So reinforcement learning, again, is a technique where you don't necessarily have at your disposal some samples that come from some given experimentalists, but it's something where you are interacting with the environment, for example, your quantum experiment or your street, and you are getting some stimulus, so some response from the environment in order to improve your current strategy. So I cannot go into the details of how this works because it's a relatively complex topic. We've seen a very nice tutorial by Dries Sel during the conference. I invite you to, during the program. I invite you to look at it, the recorded version. And there's been a lot of work in this direction pushed, for example, by Marin Bukov, Dries Sels, and all the crew in Boston in the group of Polkovnikov and Pankaj Mehta. Okay? And they have shown that using this basically reinforcement learning and defining as the quantity that you want to optimize the fidelity. So basically the fidelity at some fixed total time t between your evolved state at time t and your target state, right? So if you consider this as the quantity that you want to optimize during your driving, you can use this reinforcement learning to generate a possible set of trajectories that will best drive you at this target state. Okay? This is roughly speaking the idea. Then I invite you to look at the details in the papers. And a very nice thing that I found is that there is, in this control space, somehow phase diagram, a region in which, let's say, if the total time that you have at your disposal to prepare the system is not large enough, basically your final fidelity, I mean, for all the algorithms you can try, including machine learning, will be basically 0. So this is 1 and 0. So you will have a final fidelity which is small, simply because you are not given enough time to prepare a complicated quantum state, right? And also, I mean, this is somehow not surprising. If the time, however, is larger than what is called the quantum speed limit, you can see that the fidelity approaches the limit of 1. So you are in a somehow under constrained regime where you can easily approach the target state, and also doing that with reinforcement learning will give you a good solution. The interesting thing is that in the middle there is so this is the over constraint. This is the under constraint, if you want, but potentially with a very long time. Then in the middle there is a whole interesting region of glassy behavior, where basically preparing the ground state will require some effort, in the sense that finding the optimal protocol that will drive you to this target state is by itself a glassy problem. So in this case, even if you have, let's say, reinforcement learning that will allow you to find a rather good solution, however, finding the optimal solution is by itself a hard problem. Okay. So this was the last somehow family of applications I want to discuss. Maybe I would like to wrap up with some final questions that we have in this field, and try what are the open problems we have been discussing also here at the conference and also at the program. So there are several open problems that somehow have been also emerged during this discussion so far. So, for example, the fundamental open question, I would say, is understanding how complex is a quantum state. Right? So, how complex is psi, right? So, psi is this exponential monster. However, we know that the properties of a physical system in most cases can be described using a much lower level description of the system, let's say mean field or some improvement of mean field. So there must be a measure of the actual complexity in general of the quantum system that somehow looking into also this neural network representation should emerge. Okay? Then connected to this is also how many samples we need to learn a quantum system. So imagine that I have an experiment. I can do n measurements because my measurement time is not infinite and my experimental friends are not willing to spend nights in the lab. So are those measurements enough to reconstruct the quantum state of, let's say, 100 particles, 200 particles? So what is the dependence of the complexity of the state on the number of measurements that I need to reconstruct this quantum state? This is an important question, especially when since we are progressing in this field and we are able to reconstruct the state, many more and more complicated states with a lot of particles, but we don't understand yet this fundamental question. So how many samples do we need, and what defines the complexity of the quantum state ultimately? And another question which I believe is also very interesting concerns somehow these applications in variational things. What I believe that would be extremely useful to have, and also as a discussion in the field, would be to have more efficient description of symmetries, of physical symmetries. Right. So by physical symmetries, I imagine the simplest symmetry you can have is translation symmetry. More complicated ones are fermionic symmetry, gauge symmetries, all sorts of physical problems that are not emerging in this world, since typically fermionic symmetry is something that you don't need when you do image recognition, right? Typical images are bosons. So in this sense, this is the contribution that us as a field can give to the more general framework of machine learning, and understanding how to enforce this symmetry directly, which is the open problem, I would say, especially for some of these, in the weights of the networks, is something that is open and that will lead, in my opinion, to, if done properly, to several breakthroughs in the next years. So thank you for your attention.
Examples where it downright failed to use a neural network as an ansatz for a quantum state? Or, I mean, obviously you can't prove that it always will fail, but where you actually had a hard time and you said, okay, let's try something else.
Well, yeah, I mean, if you take a completely random state in Hilbert space, we have cases where it's impossible to describe, to do tomography, for example. Right? So if you take a completely random state, which is basically picked at random, it does not have any specific physical, it's not the ground state, let's say, of a reasonable Hamiltonian, then the number of samples and also the size of the network that you need is too large, simply because it's completely entropic, in the sense of the information that you have.
But for structured problems, no?
For structured problems, Andrea, what's you're not big.
The paper we wrote together.
Really?
We use this family of quantum states that is where it's provably easy for a quantum computer to sample from, but where it's provably hard for a classical computer to sample from.
Yes, but those are okay. But let's say those are somehow crafted examples that are not necessarily physically relevant. So just to make a comment on that. I mean, we wrote the paper together, so I don't want. But to say that you can always find states that are, bad in the sense that they are too random or they contain too much information, and I mean, there's no way you can compress. There's no way you can compress everything. That's for sure.
When you're describing this going by passes, is it similar to just passive integration?
Excuse me, this one?
Yeah, with this picture, yeah.
No, in the sense that here you are navigating into a high-dimensional Hilbert space of your quantum states. So what did you say?
But when you're talking about trajectories,
yes.
It's, what you mean?
By trajectory, yes. Sorry, I mean that this h of t is typically can be seen as a trajectory in this parameter space of h, right? So you can say that here I'm increasing the field, here I'm decreasing it. I mean, as a function of time, I'm having a trajectory.
So it would be not like path integration itself.
Not really. No. I mean, it can. I mean, there is a parallel, of course, in the sense that all Hamiltonian time evolution have a dual in the path integral language, but not directly for what I wanted to say. Yeah.
Yeah, two questions. One is often when you do a variational method, at least in the past, one could also identify the Hamiltonian for which the variational wave function is the ground state. So if you now take, let's say, representation of the wave function with the deep network, is there an Hamiltonian for which this is the ground state and not for Hamiltonian?
There is some work going on in this direction. I would say that we know some families, for example, graph states. You can find some graph states whose exact ground state is a neural network. But in general, if you take a fully connected network, this is a hard problem to solve analytically, I believe. But there are some families that are known. Yeah, we can discuss.
I have another question.
Yeah.
No, go ahead.
Come back. Oh, I just wanted to mention, about 20 years ago or so, in the case of fermions, with finite Hilbert spaces, we gave an argument where if the Hamiltonian is just a one-body operator.
I mean this one?
Yes. As n gets large, you cannot make f go to 1 in
Yeah.
general.
No, that's why I said that this time here can be potentially exponentially large.
Yes, so that
mentioned it
you
in
could
past,
never
but-
get there, and I
Sure,
think
sure.
it's related to your ergodic.
Sure.
phase.
So in this sense, this glassy phase tend to dominate the phase diagram of this. Right.
Yeah, the purpose of our thing was sort of different, but asking the question of, can you reach any arbitrary state? And the answer will turn out to be no, right?
Yeah.
No matter how long you ran, basically.
Sure. Yeah, this is, of course, I think there are some also topological obstructions in the middle, right? So if your Hamiltonian is not powerful enough to drive you these topological obstructions in Hilbert space, then there is no way you can reach the final state. So this is a very, maybe those are connected, maybe we can discuss.
Yes,
Yes, Miles.
I had a question. So you mentioned the connection, like you mentioned how it's competing now with VMC, but you're using often techniques that are very similar or identical to VMC to optimize these in many cases. So what's kind of working better than some past things about VMC with other kinds of wave functions you've tried?
Yeah, so what Federico has told us somehow in a very nice talk for those of you who attended, is that if you use variational wave functions that are inspired by physics, so there you really need somebody who's good at writing down an ansatz which is physics inspired with maybe few 10 parameters, then standard variational techniques, Monte Carlo techniques, can immediately give you a relatively good energy or relatively good properties for these problems. However, if your problem is to solve in a better way the Schrödinger equation, then you need to use much more parameters. And in this sense, these families of parameterization based on neural networks are, to some extent, not to some extent, they are more powerful of these traditional approximations because they allow you to, in principle, extrapolate to the exact result. Then in practice, we have to fight. But, yeah.
Okay, thank you very much.
Yeah.